and precisely speaking that one doesn't have to know separation of variables. In fact, why I got separation of variables for two reasons. One for the comprehensive examination for the PhD students, another reason is for the beginners. Otherwise, separation of variables have so much of limitation. Once you learn finite Fourier transformation, you will see that separation of variables have no use, and you don't have to learn separation of variables. Why I thought? Because of the syllabus. Otherwise, even I personally do not use separation of variables. And if you want to know the precise application of finite Fourier transformation in real-life problems, you can refer to my paper. XEG Journal 2009. Okay, so this way, so one of the applications of the finite Fourier transformation has been published, and this technique has not been there in any of the books. Okay, you won't find in the textbook this technique. Only you can see in my paper and in my class notes. Because why this technique has been so powerful and the technique is so easy to implement? Because it can incorporate time-dependent boundary condition. It can incorporate any kind of generation. That means if you have a system which is non-homogeneous differential equation, NH and NHB both, which is most generalized, we cannot have anything worse than NHE and NHB combination, and that too NHB is time dependent. So we have a boundary condition which is changing with time, which cannot be solved by separation of variables. Even non-homogeneous equation cannot be solved by separation of variables. Now we can see that why I don't prefer to have separation of variables. So the equations which are non-homogeneous in nature, the boundary conditions which are time-dependent in nature, whatever the worst possibilities one could assume, we can actually look into that. And if the integrals can be, so the only thing is that entire process lies in the integral. Only the integrals should be evaluated analytically. In that case, the method will be semi-analytic. And what is the objective of the method? Because we know that finite Fourier transformation, essentially, we are actually finding out this solution, I equals to 1 to infinity. This is a technique. And where phi I is orthonormal eigenfunction. Orthonormal eigenfunction. These are nothing but orthonormal eigenfunction. You know, remember that when you find the eigenfunction, which is generally orthogonal to the self-adjoint operator, but we can always make it orthonormal by dividing by the length of the eigenfunction. So it is orthonormal. It is orthonormal eigenfunction. In fact, one of my projects, MTech projects, will be open for the finite Fourier transformation on the microwave heating. Most of the ones who can actually work on this finite Fourier transformation. You don't need to have actually any computer. Directly you can work on finite Fourier transformation. Okay. So this is the first time I applied in microwave heating in finite Fourier transformation, and a lot of challenges actually there. So once you learn it, you can actually. This method is very rare in the sense because many people do not know. That means if you actually work on this area, that's it. You can publish the world's top-notch journals, and that's what this is the world's #1 journal in chemical engineering. So what we are actually planning to discuss is orthonormal eigenfunction. Only thing is that when you want to talk about orthogonality of the eigenfunction, you be careful about the weighting function. The domain is psi I omega. If you say in the one-dimensional case, it should be Wx, which is delta. Because it is cylindrical coordinate system, for the Sturm-Liouville operator, Ws is not 1. Cartesian coordinate system, different itself, it is self-adjoint operator. L is what for the Cartesian coordinate system? d2 by dx square. The cylindrical coordinate system is not the case. 1 by r, ddr of r. Okay. So in that case, the weighting function is not equal to 1. Something else from the Sturm-Liouville operator. So when you implement the orthonormality, be careful. These are the exact eigenfunctions, not orthonormal. Okay? So this is the thing. So our main objective is to find the solution which is summation Ci phi I, and Ci is nothing but, what is Ci? Inner product U phi I with respect to W divided by phi I with respect to W. This is equals to 1 because orthonormal eigenfunction. So your Ci is nothing but U inner product U phi I W. So very easy technique, you can see that. Nothing is there in this technique. Because you know solution, which is nothing but linear combination of the eigenfunction. Solution is nothing but linear combination of eigenfunction. The solution is linear combination of eigenfunction. Only thing is eigenfunction you can find out easily. Only thing is what you need to know, the Ci, which can be obtained from this expression. That's it. Now how to implement? So here we will see the first time we will actually discuss application of bilinear concomitant, which is JUV. So this time we will see this process requires JUV non-zero. Most generally, because if you have time dependent boundary condition, most likely and most generalized means JUV may not be zero. JUV is non-zero. And that's what the challenge is. Non-zero bilinear concomitant. And in that case, arithmetic transformation works in an excellent manner. So let's look at one of the ODEs. First I will do ODE, then I will go for PD. So three cases I will discuss: ODE, one-dimensional PD, and multi-dimensional PD. And then that's all. That will be the overall point for a transformation class. I think maximum 3 classes will finish my square transformation. So a problem for the ODE. First case, d2u by dx square equals to minus fx. You can see it's non-homogeneous. Fx could be anything. U of 0 equals to g1 and u of 1 equals to g2. Everything is non-homogeneous. Okay? But if we look at an operator which is self-adjoint, d2 by dx square, operator is self-adjoint. Operator is self-adjoint, and which is d2 by dx square. Okay. So here the interesting part is we have to find out the eigenvalue problem. That's a different approach here. Here, of course, we cannot see the eigenvalue problem here. Everything is non-homogeneous. But as I said, any function can be expressed as a linear combination of eigenfunctions. That means you have to find out the exact eigenvalue problem. So my operator is d2 by dx square. Psi n equals to what? Equals to minus lambda n psi n. And the boundary condition will take as a similar boundary operator. The boundary operator is Dirichlet boundary operator, both the situation. At x equals to 0, Dirichlet operator, and x equals to 1, Dirichlet operator. So, what will be my boundary condition then? What will be boundary condition then? Same operator as I said. Psi 0 equals to 0 and psi 1 equals to 0. Without homogeneous boundary conditions, we cannot have the eigenfunction problem. Now, this type of problem we already have seen. This type of problem we have already seen. What is that? What is the solution for psi n? Psi n equals to, we have done it. We have done 1000 times, I think. We have done 1000 times. starting and nobody is telling me the answer. What is psi n? What is that? A n sin n by x. What is lambda value? Lambda is n square pi square. What is phi n then? Orthonormal eigenfunction. What is phi n? This is the eigenfunction which is orthogonal. Now we have to find out orthonormal eigenfunction. Phi n is the orthonormal eigenfunction. What is that? Don't assume something, please do it. It is not that straightforward. You have to divide by the length of the eigenfunction. You remember how to find the length of the eigenfunction? How to find the length of the eigenfunction? Psi n divided by what is that? Norm. How to find the norm? Don't say norm or not. Can you tell me how to find the norm of the eigenfunction? Arbitrary are saying norm. That any kid can tell that. How to find the norm? Don't say norm. I want the exact expression. What is the denominator term? What is that denominator term? Nikita. Integral 0 to 1. A n sin n by x whole square dx whole to the power 1 by 2. Yes. Now tell me the answer. Now tell me the answer. How much is your ortho? What is the expression for the orthonormal? Now we'll see. Orthonormal eigenfunction is unique. It does not depend on any of the integration constant. What is phi n then? What is phi n? Simple integration, people are looking at somebody else's notes. I am just seeing the kind of class I am actually teaching. People cannot even do the integration also. How to do the integration then? Nikita? How to do the integration? Down? How? So directly you can do that. What's the formula for that? Cos 2x? 1 minus 2. Even this simple formula we don't know. What we can do that? What's the next step of the integration? 1 by 2, yes. 1 by 2 and then multiply by 2, you get 2 sin square n pi x and then 2 sin square theta, the formula is there. If you put the formula, what is the final answer? My God, this kind of 10 plus 2 level of math I have to teach in the class. What's the final expression? Huh? Yeah, something you're saying, I think looks like correct. What is that? Root over 2? Root over a. A and a will get cancelled. Then what is that? What is that? A should not be there. A will get my God, it takes so much of time. Root 2 sin n by x. Now you can see what is the advantage of working on the orthonormal eigenfunctions. The orthonormal eigenfunction concept was not there in separation of variables. Okay. Now, what is that? Your solution procedure is Ci phi ix, and you have to find out the Ci. Phi i's are obtained, right? Phi i's are obtained. So now phi is unknown. If you know CR, you know the solution. So nice. So what you do? d to u by dx square equals to minus fx. d to u by dx equal to minus fx. So take inner product. Taking inner product with respect to phi ix. That means we have to take d to u dx square phi ix equals to minus fx phi ix. Am I correct? I am taking inner product both sides. So what you get? Here, of course, the orthogonality criteria, if you want to implement, if you see that the weighting function is 1, right? The weighting function, so the inner product will be defined with respect to weighting function 1. So here Wx equals to 1. If it is something else, you need to put different Wx. So Wx is very important. So whatever the orthogonality criteria for the eigen function, the same Wx has to be taken here. Okay, remember that. Same Wx has to be taken here. That means if I have the operator from cylindrical coordinate system, your Wx will not be 1, it will be something else. Please note down that part. This kind of problem may come in the final or in semester. So we have 0 to 1 d to u dx square phi ix dx equals to integral minus 0 to 1 fx phi ix dx. Okay. Now what is the objective? This kind of derivative we have seen earlier in the adjoint theorem. Adjoint theorem, what we have seen? Inner product. LUP, you got U L star V plus JU, right? Okay. So I want the final answer here. That part you already know. You tell me the answer. Now this pi and pi plus pi, everything is known by us. Just everything is known to you all. So you have to give me the final answer for this part. So you know that what should be taken as u, what is taken as v. ddx, du dx, and you know that how to find that ddx of ub is u dv dx plus v du dx. And here u dv dx is v du dx is given. So in that case your solution will be ddx of ub minus u dv dx, or whatever is actually given. So we have seen that u dv dx is nothing but ddx of uv minus v du dx. The main objective is what is your u, what is your v. Once you know that, that's it. You can actually split up and get the final form. What is the final form? What is that? First you tell me the bilinear concomitant. I want the bilinear concomitant. How many terms will be there? Bilinear concomitant. How many terms will be there for the bilinear concomitant? How many terms will be there for the bilinear concomitant? All people have forgotten what I have taught in the class. What's happening? What are you doing here? What are you doing here? Do you understand bilinear concomitant? What's the next step then? Divide something, right? Go to the last page, extreme last page, and don't sleep. I'm getting very angry. You know what I can do? I can finish your video. That power I have. You want that way? You want it that way, right? Yeah. So go to the last page, extreme last. Yes. What is that? Bilinear component first. What is that?
u by dx.
Yes. U dx phi ix
0 to
1, then
1 minus
du dx phi ix 0. I don't do shortcut. Next,
minus u d phi by dx
minus u d phi I dx 1 plus
plus u d phi by dx
dx 0. Then
plus integration 0 to
integration 0 to 1
u d2
phi I u d2 phi ix dx equals to that's it, right? Equals to minus 0 to 1 fx phi ix dx. Am I correct?
yes.
Now if you look at this phi I is nothing but coming from eigenvalue problem, where phi ix at 1 equals to 0 and phi ix at 0 equals to 0. The eigenvalue problem is what? See, psi I is an eigenfunction. That means phi ix is also eigenfunction, right? And your eigenfunction problem can be written also orthonormal eigenfunction. Is orthonormal eigenfunction. Okay. So this term should be going to 0. This term is going to 0, but these two terms are not 0. What is u at 1? G2t. G2 u of 1 is G2 and u of 0 is G1. Okay. So we first evaluate JUV. So this is your nothing but this entire thing is JUV. This entire thing is JUV. So JUV first two terms are 0. Your phi ix is root 2 sin n pi x. Phi I prime x equals to what? Phi I prime x equals to root 2 n pi cos n pi x. Phi I prime at 1 equals to how much? And phi I prime 0 at phi I prime at 0 equals to how much? Which is root 2 n pi. It's quite obvious. Cos 0 equals to 1, right? So it is root 2 n pi. But if x equals to 1, it will be cos n pi. What will be that then? What is that? Cos n pi, you can actually have the numerical value. What happens to your brain these days? Minus 1 whole to the power n. Minus 1 whole to the power n. Root 2 n pi. Okay? So you got the phi I prime. So what is your JUV then? What is your JUV? Root 2 n pi. In the bracket something will be there. What is that? Root 2 n pi in the bracket. Something is there. What is that? Root 2 n pi in bracket JUV. This should be JU phi I should say. Generally our formula wise I know it should be JU phi I. It's better. Root 2 n pi into what is that? You are telling something, Nikita. G1 minus, yes. Minus 1 G2, right? Okay, very good. Now coming back to the main equation, you have JU phi I. What you can substitute this one? So you know that d2 phi I dx equals to minus lambda I phi I. Okay? Phi is orthonormal eigenfunction. Right? Phi is that. So remember that if I have AUI, lambda I is vector space. If UI is the orthonormal eigenfunction, it's okay. Doesn't matter. It's better even. Because same vector, only the length is 1. The same thing here. So it is eigenfunction, it is orthonormal eigenfunction, same equation you value. Right? Same equation will be valid. Because what is the relationship mean? Psi ix is nothing but divided by some length equals to phi ix. And if you take the derivative, you will see the same differential equation you are getting. That's how you can prove again. Right? Psi ix by 8 is phi ix. If you take d2 psi I by dx by d2x square, you will get d2 phi by d2 phi by dx square. Right? Okay, so what will be the next term then? This term. U d2 phi by dx square. What will be that? We have done this kind of problem. d2 phi by dx square will be replaced by minus lambda. So it will be what? It will be what then? Minus lambda I. It will be replaced by minus lambda I phi I. So it will be inner product. Am I correct? Lambda u by u phi I, right? Am I correct? Equals to minus f phi I. Am I correct? So what is your u phi I? Which is root 2 n pi g1 minus 1 to the power n g2 minus a plus. Is it minus or plus? Of course plus. Okay. So you got inner product u phi I equals root 2 n pi. G1 is known, G2 is known, f is a known function. This phi I can be evaluated. U phi I is what? Ci, which is u phi I. Ci is nothing but inner product of u phi I. You got the solution. So solution is u equals to summation I plus 1 to infinity inner product u phi I is what? Phi. That's it. What is that? Divided by? Okay. Okay, this should be lambda. U phi I whole divided by lambda, right? Whole divided by lambda. Is that okay? So now you can see that this G1, G2 could be any condition, right? Now the thing is that this does not matter what kind of boundary condition you have. Only thing is, if f is a very complicated function, you have to evaluate this integral by Gaussian quadrature. In that case, this Pioneer transformation can be applicable for any sort of any type of problem. In that case, Pioneer transformation can be applicable for any type of problem. Right? Any questions here? Any doubts? Any questions? Gaussian quadrature. What is this f phi I? So I am now giving you a real life problem. d2u by dx square equals to minus sin x e to the power x. Boundary condition u at x equals to 0 is e to the power x to the power cos x. U at x equals to 1 cos log x. Your G1, G2, right? So G1, G2 is substituted here. Okay? And then, now what is your f? Sin, not minus. Minus is already incorporated. So if, because the original differential equation is what? ddu by dx square minus f is. So f is sin x into the power x. So integral is f phi I integral 0 to 1 sin x e to the power x and then which is root 2 sin can you evaluate this integral analytically? Of course not. It will be very difficult. In that case, you can do by Gaussian quadrature. That is the only complicated part. So this method will be applicable for any problems, even the complicated boundary condition. And the worst thing is that the final integral can be evaluated numerically. That's all. So any problem you give it to me, I will just get the analytical solution. Only part is that this integral, sometimes you will not be having the analytical solution. In that case, you can do by, now you know Gaussian quadrature. So if you know Gaussian quadrature, it's not an issue at all. Okay? Any doubts? Any questions? Any questions? Only thing is that here you can just do slight correction. You put I pi x, it is better. Always you are putting in terms of I. So that we can easily do the summation part. Remember that summation is taken in terms of 1 to infinity. I put n for your convenience, but I think we have to put I. Otherwise you will be really lost. Okay. Sometimes we actually see, it's quite often we write phi n, sometimes we write phi I. It depends on what index you are actually using. Whatever index you use, this should be consistent. Okay. So please correct that part of it. Root 2 I pi should be. Because in that case you have to implement. In fact, for example, I want you to have a solution of this. I want if you can get me the solution of this kind of problem. Next class it will be wonderful. I just want the solution. In fact, when you have the summation term, next question is how many terms will you consider? Roughly 10 to 20 terms. In fact, if you are lucky enough, with 10 terms you can get the converse solution. Okay? Because strictly speaking, infinite number of terms are required. But my personal experience is more than 10 terms is okay. If you take 10 terms, it will be fine. 10 terms will be fine. Okay? Next, we will be going to the partial differential equation. Next, we will go to the. So this part is clear, right? Okay. So try to solve this type of problem. Or you can actually do one thing. Other thing is that if you want to really benchmark your problem, there are a lot of problems actually available in your textbook. You pick up any of the problems where the solutions are available by your general situation. General situation means many ordinary differential equations are available in your books. Okay? In that case, you can actually, for example, now I will actually tell you how. I'll give you a problem. d2q by dx square plus 3du dx 2u equals to say 5x square plus sin x. This type of problem we already discussed. This we did by complementary function particular integral. Right? Say ux equals to 0, 0 and u x equals to 1 equals to 2. This type of problem you can pick up. Identify the operator. What's the eigenfunction problem in that case? If I want to solve by finite approximation. What's the eigenfunction problem? This type of problem, next class will be on next Tuesday. So what I am giving you this entire week to practice this type of problems in your Grewal's book. Each of the problem can be solved by finite approximation. If you do that, you really expert in finite approximation. Okay? How to solve? How to get the operator for the eigenfunction? What's the operator for the eigenfunction?
d2 by dx square plus d2 by dx square
d2 by dx square
plus 3d by dx
3
d by dx
d5 by dx.
5 by dx.
But I won't do this way. I won't do why? First thing is Sturm-Liouville operator. Otherwise, you don't know what is your Wx. We'll do sum liquidity operator. What is your sum liquidity problem here? ddx of px due dx. What is px? What is your px? So corresponding eigenfunction problem is d2 phi I dx square plus 3d phi I dx plus 2 psi I equals to minus lambda I psi I. But we won't solve it. We may solve it, but thing is that we want to know what is Wx. So what is the corresponding sum liquidity operator? Otherwise you know Wx. If you know Wx, you cannot do the eigenfunction orthogonality. If the orthogonality is wrong, everything is wrong. If orthogonality is wrong, everything is wrong. If orthogonality is wrong, everything is wrong. What is px? So it will be ddx of px d psi I dx plus qx d psi dx minus lambda I wx. You know that, right? What is px? What is that? I am not able to hear. Anybody raise the hand and tell me the answer? What is px? What is px? Come here. What is that? E to the power 3x. Then plus qx 2 e to the power 3x. Okay, I don't have the answer. And then minus lambda I wx. Remember the 2 is also there. Is it taken care? Okay. What is wx? What is Wx? So, I don't want to solve it. I think this is the procedure to solve it. You go back home, try to pick up this type of problems and solve by the finite transformation if you want to learn more on that. What is Wx? Did you get it? What is that? 4 e to the power 3x. Okay. In that case, what we orthogonality criteria? You look into it. Next time I will discuss it. Next, we will be talking about the PDE, partial differential equation. Dou u dou t. Dou to u by dou x square plus fx. Non-homogeneous type equation. The parabolic PDE, right? This parabolic partial differential equation. Ux equals to 0, which is u0x, u0 comma t, which is g1t, u1 comma t, which is g2t. You can see time dependent boundary condition. First time we are introducing time dependent boundary condition, non-homogeneous equation. So it is NHE NHB type. It is NHE NHB type. Time dependent boundary condition, non-homogeneous equation, and we'll show that this has also analytical solution. Okay, so now the thing is that in a space, one way we are lucky, in the space we have only one space, hence there is no y. So in the space generally, so what we actually do that, this type of problem we can express as Ci phi ix. But if you look at which is ux comma t, the function of x and t, the Ci should be, this phi I cannot be a function of t. It's eigenfunction which cannot change with time. Eigenfunction cannot change with time. Eigenfunction, the basis function, cannot change with time. So Ci should be the function of Ci should be the function of time. Right? Ci should be the function of time. Okay? So we have to find out CIT. And what is CIT? Which is inner product UXT phi x. Inner product UXT phi x. What is now phi x? What is the governing equation for phi x? Eigenfunction problem. eigenfunction in x direction. In the x direction, what's the operator? Dou 2 by dou x square. That means corresponding operator for the eigenfunction in x direction will be dou will not be there. X direction, eigenfunction, x direction, phi I x is only ordinary derivative. d2 psi I dx square equals to minus lambda I psi. Okay. What is the boundary operator? As I said, the similar boundary operator we have type. If you look at x direction, which is 0, the Dirichlet boundary operator, so it will have the Dirichlet boundary operator, homogeneity, and that's the way your eigenfunction problem in the x direction. Not clear? So eigenfunction problem can be easily identified for any kind of differential equation. You have to look at the particular direction. What's the operator for the partial differential equation? You have to find out the particular direction. What is the operator? The operator is dou 2 by dou x square. It will be nothing but d2 by dx for the eigenfunction problem. And in that case, what actually happens? You have to see the boundary operator. The boundary operator is the Dirichlet boundary operator. The Dirichlet operator, same Dirichlet operator actually do. And we have seen this is nothing but psi I equals to ai sin I pi x. I am taking in terms of y. Otherwise, like last problem, we have confusion. Right? That's it. And what is your phi I? Orthonormal eigenfunction? We have found out root 2 sin I pi x. That's it. Next step. What is my next step? What's the next step? Next step is what? Same procedure for the effective Weinberg transformation. Inner product, which is dou u dou t minus dou 2u dou x square. Or you can actually, what you can do, each term we can take inner product. Phi I x dx 0 to 1, 0 to 1 dou 2u dou x square phi I x dx plus 0 to 1 fx phi I x dx. Am I correct? Yes. Next. So this is my term 1. This is my term 2 and this is my term 3. What is my term 2? Term 1. If you look at the term 1, which is 0 to 1, dou u dou t phi I x dx, which you can write as d dt 0 to 1 u of x t phi I x dx. If you don't understand, try to get back this step. Remember that phi I x with respect to t is constant, is only function of x. If you take derivative of this, ddx of qv, v is constant because it's not the function of time. So it will be du dt or dou u dt. So that means this is nothing but ddt of inner product u phi I x. Am I correct? Is nothing but inner product ddt of. So what you have to find out? To find out is to get the solution. The solution is CIT is nothing but inner product of this. If you find, your job is done. First term is over. Second term, inner product 0 to 1 dou 2u dou x square phi I x dx. You know the thing, just now we have done it. Just now we have done, you will get bilinear concomitant and operator. Just now we have done it. You should be telling in 1 minute. It is there in your notebook. Just now we have done it. Just now we have done it. Just now you have done it and you will not able to get the answer. What? You are just arbitrarily guessing. Huh? What is the first? What are the binomial concomitant here? Come on, the way you are actually giving the blank face as if you are just talking some Hebrew. What is that? You cannot get from your notebook. Just now I have done it in the previous problem. Only difference was it was do, it was D, now it is do. Even a kindergarten kid can get the answer by replacing D by do. See the situation. I am really stunned that the entire class is silent. Come here. Pardon? What? Just now I did the binomial concomitant and everything. The previous problem. I am really shocked. Dou u by dou x. See the situation of yours. What class I am teaching? Phi I x 1 minus dou u dou x 0 minus u dou phi I dou x, or it should be d phi I because it is only a function of this 1 plus u d phi I dx 0 plus it will be integral 0 to 1 u d2 phi I dx square dx. So simple. Nobody could tell the answer. It was done in just previous class. And now if you look at the boundary condition, phi I x at 1 equals to your eigenfunction problem says that 0 all 0 0. U equals to which is g2t, right? This is g1t. d phi I dx, everything is there. So second term will lead to what? Minus g2t phi I prime 1 plus g1t phi I prime 0 minus lambda I inner product ui phi I. Like same way. Next third term is actually quite straightforward. Is there, we don't do anything. So now we will be combining first, second and third and we will be showing that it is nothing but dy dx plus dy equals to q. Next class actually I will discuss. One thing I am telling you that in your, I think some of the assignment I have given a lot of differential equation and can be solved by eigenfunction approach. Problem number set 7. Problem number 7, set 7. Problem set 7 for A, B, C, D. For A, B, C, D. For A, B, C, D. Did you see that? I want some of you to submit the comparison. It is asked for the eigenfunction problem, right? You solve eigenfunction and the finite square transformation. If you do that, you will really knowing only these 4 problems you solve, you will be expert in at least some of the part of the finite square transformation. So I will see you next Tuesday because Friday and Monday